She will match Fortey this time in comparison to her age, which is the summer.
Well, thank you very much, Derek. Yes, I'm going to talk about trilobites tonight, and to a certain extent, this is a review of some of the research I've done over the last 35 years or so. We're quite often used to seeing, and I've published books showing these sorts of reconstructions of animals, trilobites, scuttling around on the seafloor, in this case of the Devonian. And there's a sort of feeling about these that they're somehow well-known reconstructions of actual life habits. But of course, they're all the subject of scientific deduction. And what I'm going to explore a little tonight is how the science behind how you deduce how completely extinct organisms, like trilobites, actually lived, what they did, the different places they lived, and the different livings they made in the oceans. Of course, they're entirely extinct, so we have to use different lines of evidence if we want to try and bring them back to life, as it were. I'm going to start by showing you a photograph by Derek Civita, who's well known in the trade as taking some of the best trilobite photographs there are. This is a sort of fairly middle-of-the-road kind of animal, a trilobite called Calimene. I want you to see, just to give you three terms, or a few terms to hang on to in case you don't know about trilobites. They had, here are the three lobes lengthways into which they're divided, but they're also divided into a head or cephalon, a thorax here, composed of a number of segments that articulate so that the animal was flexible, and at the back end there's a tail or pygidium. A lot of trilobites had eyes, and most trilobites had fairly small or middle-sized eyes placed on either side of the head. And here they are, here and here. Many trilobites became blind, but it's thought that that's usually secondary. So if that's your kind of middle-of-the-road trilobite, what we want to do first is explore some more extraordinary-looking ones, because so often in nature, the more extraordinary-looking ones are the ones that it's easier to deduce something about how they actually lived. This is a journey down memory lane for me, because I'm going to start with this one, which is the first trilobite I ever named. Now, trilobites are normally found like this in bits, rather than lovely whole specimens, and this was the first trilobite plate I ever published, I think. And I called this animal Opiputa, which means one who gazes. And the reason I call it that is because it had the most enormous eye, or eyes, on either side. You remember those little ones that the Calimene had? Well, that's the eye of Opiputa. That's the eye of Opiputa, and it fitted on either side of the head here like two kind of enormous headlamps on either side of the animal. And also, how does this differ from Calimene? Well, you'll notice the thorax is long and thin, narrow. The lateral parts of this animal are shrunk down to virtually nothing. So it's a long, thin trilobite with enormous, great goggly eyes. Well, obviously this is doing something special. And some of the early work I did was to try and work out what that was. And I deduced that this animal, far from living on the seafloor, like that early reconstruction I showed you, was probably part of the pelagic community, where there are a lot of arthropods which have these sorts of features. This is a trilobite trying to pretend to be a pelagic shrimp, if you like. He's a bit slightly contrasty on the screen here, but I hope you can make out. This is another unrelated, but still planktonic or pelagic trilobite, in which you can see the eyes still in position. There's one there, and there's one there, just showing you that the whole area that was available to be a visual surface in these creatures was occupied by eye. Now, you can look in the recent ocean, and this is one way you can work out life habits, if you can find something that seems to be a suitable analogy. Again, we're not talking about relation here, we're just talking about something with a similar adaptation. This is a very old illustration, but it's a very nice illustration of a particular amphipod crustacean, in which I hope you can see the eyes also have become enormous. They occupy almost all of the area of the head that they can. And this is an ocean-going amphipod that lives in the water column. The other thing you can do, of course, is you can work out, because of the way the trilobite eye is constructed, where these animals were actually able to see. Now, most trilobites, Calimini included, the ones that lived on the seafloor, had a field of view that was predominantly lateral. They looked from side to side, like this, like this. Because they were on the sediment surface, that's where most of the items of interest lay, where they might be attacked by predators or where they might find their own food. By contrast, the ones that went up to live in the water column had 360-degree vision. They could see all round. They had eyes, lenses that faced in all directions. I eventually went on to study a number of trilobites with this sort of adaptation, and here they are all kind of summarized together with these vast eyes composed of very, very many lenses. I actually counted the lenses rather foolishly. I blew up an enormous photograph and pricked them with a pin, you know, to 1, 2, 3, 4, 5, 979. And I think I sneezed at 2,797 or something. I had to start again. But what you can see here about the vision, imagine that made out of thousands and thousands, literally 5,000 lenses on each side. And you'll see that this animal, with lenses facing out towards you here, could see upwards. It could also see sideways. That's the side view of one of these creatures, of two of these creatures. In fact, that one and that one. So that's now looking out towards you. And if you can imagine that eye bulging outwards, you can also see it could look downwards and forwards and indeed backwards because of having that very narrow body. So these really did have 360-degree coverage. So whatever was predating on them could be spotted in advance, and they could take some sort of protective action. You'll also notice they have spines. The thorax, this part, is suspended above the head. And the spines, which are normally flat on the sea bottom, in this case, hang down below the rest of the animal. So it's a very likely sort of shape to be living out there in the open ocean. Furthermore, some of these creatures, when they evolved, actually made their eyes, that normally two separate eyes, fused together into one kind of enormous headlamp at the front. This is one such creature, or rather two such creatures that did exactly this. You see here how the eye is fused at the front. So this animal was probably preferentially seeing forward as it swam through the water. And this happened not just in one evolutionary line of trilobites, it happened several times, which, you know, is definitely an indication of a special adaptive purpose. So here we are, we've taken the trilobites from the seafloor and we put them up into the water column as swimmers. So we're beginning to have some idea that they didn't just do one thing, they were doing several things. And the trilobites, of course, overall have a fantastic variety of morphology, a fantastic variety of shapes. So you'd expect them to have many different sorts of life habits. And this is just one way that you can gradually unpick what those life habits were. So these are probably, I think, probably pelagic rather than planktonic trilobites. I should have mentioned at the outset, they're all rather small, these animals so far. They're all about just a few centimeters long, about the same size as a shrimp, really, or one of those amphipods. So there they are, occupying some space in the water column, way back in the Ordovician, more than 400 million years ago. So this is part of the reason for their success. They obviously expanded into more than one habitat. When did they first do it? Well, I just very recently wrote a paper, just a couple of years ago with my friend Adrian Rushton, finding the earliest example we could of this particular shape in the fossil record, and it's in the middle part of the Cambrian. So not far after the famous Cambrian evolutionary explosion, the first of the trilobites took to the open ocean. These are mostly working with rather unpleasant fragments compared with some of the ones you'll see later. Just to show you one swimming out of the screen towards you, those are the eyes, there and there. And Normally, those at the front, possibly, can you vouch for the fact that you can see little lenses there? Nodding heads, good, because the people at the back will just have to believe you. So that's looking at you. Well, of course, there's another question you can ask about things that are living in the water column over the ocean, and that's how deep they were living. Because in recent oceans, we have things that live in the surface waters, epipelagic, and we have things that live deeper in the twilight zone. And some things, of course, actually move up and down. Actually, you can attack some of these questions using fossils too. You see, there are two, from geological grounds, the kind of rocks in which they're found, I'd wondered about two different sorts of trilobites, both pelagic, living in different habitats. Epipelagic ones here, a genus called Carolinites, actually was found in shallow water sediments here in the inside part of a continent, but also in deep water sediments off the ancient continents. And I concluded that they probably lived in the surface water, so they could be found in all different sediment types. Whereas this chap, Pricyclopyge, which is the one you've just seen swimming out at you from the screen, probably is only found in deeper water sediments, and so probably lived only at depth. It was mesopelagic, rather than extending up into the upper part of the water column. That's fine, that's just rocks. Can you actually go to the animals themselves and do some experiments or something to offer independent evidence? Well, yes, you can. And I had a young postdoc called Tim McCormick to help me do this. We found very perfectly preserved eyes of both of these creatures, and actually there's a horrible formula in there, which fortunately you can't see, for something called the eye parameter, which on recent crustaceans and other insects varies according to ambient illumination. Tim spent a long time measuring things on trilobite eyes between the individual lenses, using very accurate microscope, measuring things like the radius of curvature, the angle between lenses, the angle between the center of lenses, and so on, in order to feed it into that ghastly equation. We can demonstrate the results schematically. This is the eye of one of the deeper water ones, which, as you see, is mostly green. That's the eye of the epipelagic one, according to my presumptions, which you'll see is mostly yellow. And if you put that onto the graph for the living organisms, the greens are down there with the dim light insects and deep water crustaceans, and the yellows with diurnal marine crustaceans and more shallow water insects. So by using 450 million year old fossilized trilobite eyes, we were able to tell something about the daily life of the animal, which I rather like. Then there's a second sort of trilobite that was found alongside and with with the dim light, the deeper water pelagics. And it's very different looking. It's much larger for starters. Some of these get to about this size. And they look very different. They still have big eyes, but some of you may be able to see the big eyes are tucked into the side of the head rather than sticking out like those great big sort of inflated balloons. This animal also has the whole head, there's the head, is smoothed out and prolonged into a kind of bullet shape. You can see sideways here the lateral view of the animal. It looks almost like the nose of a dogfish. And the back end here has a tail which is actually dished. And this is probably a well-streamlined shape. I showed it to a hydraulics expert that I know who confirmed this, and we thought we'd test it by building some models and testing them in a flume tank. We did some very simple mathematics, the kind I like, much simpler than the last. you can just put a model in, and this I did a long time ago, and you can put streams, permanganate streams, past it to see what kind of streams you get off the animal. And that's the allegedly well streamlined one, cast from a real animal. You can see the dogfish-like nose at the front here, beautifully streamed. Or you can do actual measurements by suspending this model and measuring the deflection that you get when you put a current past it. And some really quite simple mathematics give you a sort of drag over the surface of the animal to assess whether or not it's well streamlined. And there's a model waiting to go. I did these experiments up at Imperial College a long time ago. So that's actually a poorly hypothesized, poorly streamlined animal, which is, we had a number of controls that we did on this. And here's the experiment up and running. I hope you can see that all right. So the trilobite's actually in there. There's a microscope over here to measure the small deflections on the ring, so you can't actually see the trilobite now. You'll see the water in the tank, I hope. And it's a story I've told before, but I used to smoke at the time, I'm afraid. And when the experiment was going, I thought I'd better nip outside for a quick cigarette. And when I came back, the entire floor of the laboratory was about a foot deep in water because I'd switched the water supply on at too vigorous a rate. And so I thought I'd be drummed out of Imperial College and never allowed to return. But the lab technician actually came in and said, "Oh, don't worry, mate, it happens all the time." And he went to the middle of the floor and pulled out an enormous sort of bath plug. All the water gurgled away, leaving my experiment running away quite happily, which fortunately worked. We did a number of controls of trilobites of the same sort of length, some of them even looking smoothed out in the same way, but only one really performed well under these circumstances, and that was the well-streamlined one. So, in this mesopelagic environment, this deep water environment, we got some swimming trilobites, but those are the ones with the great goggly eyes, and they're very small. And that sort of circumstance, there's no way they were particularly well streamlined. They were probably relatively rather sluggish. Those big goggly eyes were not designed to cut efficiently through the water, and they were probably in the same habitat, these well-streamlined, probably much faster swimming trilobites that probably swam by main force because they had quite thick muscle attachments for the legs. I suspect they were vigorous, very vigorous animals. Both living together in the water column in this habitat. What did they do? I never published this, by the way. They were, at that size, well-streamlined at that time, they probably were predators, and there were things for them to predate, possibly the poorly streamlined trilobites, of course, but also ancestors of today's shrimps, which were also around at the time. So it was the jaws of the Ordovician. Okay, so that's one vision of one aspect of the daily life and life habits of trilobites, and we've taken them from the seafloor, or some of them, and put them in the water column. There are other things you can infer more or less directly just by looking at specimens. For example, trilobites grew. I'm not going to go into a lot of detail about this today because we know a lot about it, but a lot of it's a matter of fine detail. Well, they molted. They grew by molting like other arthropods, and they seem to have had a virtually continuous gradation from very, very small to the adult. And in that respect, they're like, I'm sure you can all recognize this animal, even at that size, the living horseshoe crab. And here's a growth series I've just recently acquired from a gentleman working in Hong Kong, living horseshoe crabs, molt by molt, all the way through to a breeding adult. Trilobites did something similar. They grew by addition of segments. In fact, having started life as a little tiny millimeter-long disc, so-called protaspis larva, which has no thoracic segments at all. So this is a sequence, famous sequence, done by somebody who was still very much around when I joined the trade, Sir James Stubblefield, in a paper written in the 1920s, in which he showed more or less exactly how this growth happened. He recognized the continuous series, analogous series, if you like, from larva to adult of a little trilobite, never got very big, never more than a few meters long, called Shumardia. And he showed that the first of all, little single disc, and then the head and the tail divide, as it were, and then the thoracic segments get added progressively by being released and pushed forward from the back end of the animal forward as the animal grew. And we do actually know an enormous amount of detail now about trilobite growth from larva to adult. When they get to a certain number of thoracic segments, most trilobites then stop adding segments, particularly younger ones. The segment number is fixed, so they get bigger, but they don't add extra segments, like those two. So there's a stage where they're growing and adding segments, and then a stage when they're just continuing to grow, which makes people ask, next question, how long did they live? Well, I suspect these little chaps probably had a single season. But there are trilobites, the biggest ones known, which are, well, not quite a meter long. They were considerable animals, and they must have taken years to get to that size. Well, Limulus, which I've shown you, takes a dozen years to get to breeding size, and some of these animals certainly took that long and probably a great deal longer. Just to show you how well preserved these larvae can be, this is just a little 1 millimeter long trilobite larva taken on the electron microscope. The little proto-eyes are here and here, but this thing is so tiny it hasn't even yet got a division between the proto-head and the proto-tail. Of course, we can compare this with living crustaceans like the cirripedes, the barnacles. Quite a number of primitive crustaceans also have little tiny pelagic larvae for dispersal called nauplii. Here are two examples here. Some of the nauplii look very different from anything later, and some trilobite larvae look very different from the adult, and it's possible they lived rather separate existence as part of the plankton and had a sort of metamorphosis when they went onto the bottom. I seem to have skipped one. So that's my attempt with Brian Chatterton to reconstruct what a trilobite baby looked like with its limbs put on. Because, of course, mostly what we have with trilobites is just the dorsal carapace, the hard part made of calcium carbonate. And that calcification went on in most trilobites right back to the larval stage. So they had eggs, pelagic larvae in many cases, and grew molt by molt to become adults. We also know, of course, that they had eyes. They've been very, very extensively. In fact, today I brought with me a PhD thesis I'm examining just on trilobite eyes and vision. And again, we know an awful lot about them. I've already told you about the field of view of those pelagic trilobites. This is a typical bottom-dwelling trilobite's eye of one kind, the holocrol eye, which are composed of very, very many very tiny lenses, which I think you can probably see even at the back in files. That's top, that's bottom, and if you think back to those pelagic forms, you can see that these lenses didn't, of course, look downwards. They had some view upwards, but mostly they were looking sideways. And when I say looking, that's how they worked, because each lens is composed actually of the same or very similar material to the rest of the calcium carbonate skeleton of the trilobite. These were animals that used calcite as the visual medium. And they did so rather cleverly by orientating the calcite crystal in a way such that light could pass through more or less normal to the surface of each individual lens. And this thesis I'm examining has shown that this is even in organisms more than 300 million years old, 400 million years old, this is happening almost at a subcrystalline level, the organization of the calcite, the orientation of the calcite threads. So, just because it's old doesn't mean to say it isn't sophisticated. It's extremely sophisticated. A typical bottom-dwelling trilobite looks mostly sideways over the sediment, as I said, and that's a typical eye of that kind. Well, we also, there's a section through just one of these eyes to show the individual prisms which are acting as lenses for these animals. But there's a much more complex kind of eye, called the schizochrol eye, which is characteristic of one particular group of trilobites, in which the lenses became even more complicated. They became biconvex, really looking much more like a conventional lens, if you like, with little baffles between. And in the base of each lens, it's now, and this is what this thesis is about, there's a little bowl which has been etched out here. Is that me? Oh, God's sake. Excuse me. I'm just going to have to kill it. Nobody ever rings me. I can't imagine who knows my number. There we go. Where was I? Yes. The little bowl. Yes, the little bowl has the calcite, the calcium carbonate, has extra magnesium in this little bowl, which is designed to help correct spherical aberration, which normally troubles rather strongly biconvex lenses. And this thesis, I haven't got to the end of it yet, there's been a little bit of dispute about that, you know, from Haas and Bruton. But the thesis has come out strongly in favor of the fact that these bowls really work. They've computer modeled it, and so these were fantastically sophisticated eyes that were probably able to use very, very low strength incident light as well. They could be crepuscular animals or daylight animals if they wished, perhaps even nocturnal in some cases. That's a section through one of these very, very sophisticated eyes to show you some of the internal structures, which I haven't got time to go into detail, that these things have, these so-called schizochrol eyes. So we're talking very, very sophisticated animals here. Incidentally, all the schizochrol animals were bottom dwellers. I don't know of any pelagic animal with that sort of eye. And there's a typical animal, you might say, with schizochrol eyes, which I worked on just a few years ago, from above. And there, apart from having slightly larger eyes, it looks a little bit, perhaps, it's rolled up, which is why it's disappearing off the screen, which is another thing trilobites could do for protection. A lot of them could roll up into little balls, or big balls. So middling-sized eyes, but if you look at it from the side, it's absolutely spectacular, or from the back. These eyes are absolutely amazing. And you can see that they're more or less straight-sided, so the eyes I've shown you so far have all had curved outlines. They've all had rather strongly curved outlines. These are, by contrast, very straight. And this is a trilobite with an eye shade. Okay, it's sticking out over the visual surface on either side, which, at least when I described it, I thought was unique. If you look at it from the side, look at that. Isn't it a fantastic thing? I think one can say without equivocation, sight was important to this animal. It's putting a lot of energy into making that eye. The question is, what was it designed like this for? This differs from most other trilobite eyes. And now I want you to think in your mind's eye back to those curved eyes and what I told you about the reception of light in each lens being normal to the surface. Okay, if you've got that in your mind. On a curved surface, it's pretty obvious. As you move away from the lens, so you're going to have a cone that gets wider for each individual lens, because it's on a curve. Yeah? Can you imagine that? One of the features of this eye, very obvious, is its straight-sidedness. Now that means that as you move away from the lens, you're still getting the same sensitivity, even when you get a long way from the animal. I've put it on a little diagram there, which I hope shows up just about. The lines are rather faint on these. You can see there's a straight-sided eye, like the big-eyed chap I've just shown you. So there's these parallel lines going through each lens. On a curved surface, they get further apart as you go away. So I can infer that that tower-like eye was probably able to see things at a distance, precisely in a way that a normal strongly curved trilobite probably couldn't, which of course makes a problem for the animal, because the further away you are, particularly underwater, the more distant, the feebler the light that gets to you. And if you're a shallow water animal, the more confusing light comes refracted from above, from the surface waters. So what do you need to do? You need to develop an eye shade. In fact, it's helping me right now to see people at the back. It's not so different in principle from when you've been on the Serengeti plains, those of you who have, and you're looking at a distant impala, you know, on a bright day. We all do it. You can test it on the trilobite quite simply, in fact, by that's shining a parallel beam of light at the side of this incredible eye. And if you take the beam and bring it so it's above the animal, at one point, there's the light, you can see it there. The whole of the eye simply goes into darkness. The shade is working, it's very effectively shading out all the light. So this was a special bottom living with eyes like that. That's not swimming around in the water column. It's an armored bottom dweller, probably a hunter, looking for distant prey over the Devonian seafloor. Now, this particular case, I think, it probably also indicates that this was a diurnal rather than a nocturnal animal. So these eyes are very special indeed. Okay, so what other things can we do? Well, we can go into the field, and geologists like to do that, and collect lots of different trilobites from different habitats, because habitats are preserved in the fossil record from inshore to deep sea. We don't very often in the old ancient rocks have oceanic habitats, very, very deep sea, because most of that's been consumed by the engines of plate tectonics. There are a few cases. But we do know that trilobites lived everywhere from the inshore. None of them went into fresh water. If they had, maybe one of them would have survived. They were obligate marine animals, but they lived everywhere from inshore to the deep sea. So you've got different habitats, all of them with their little suites of trilobites living together. And that's one of the reasons why there are so many species. This is just one section I happen to work on in a tropical environment in the Ordovician. There's an inshore lot here. There's a lot that seems to live in sort of reef-like mounds. There's another lot that lived in the open shelf, and there were even ones that lived in deep water, rather oxygen-poor environments, which I might get back to. This goes from the Cambrian through to, that's a section from the Carboniferous. So this went all the way through their 300 million year history. They lived in different habitats. Very often the ones that lived out here lost their eyes and became blind. They didn't need sight, and so often deep sea organisms become secondarily blind. So the eyes that were so important to some were lost in others. And then, of course, if you're trying to put together a picture of the world, not only have you got different habitats from inshore to offshore, you've also got different parts of the world with different kinds of organisms living on them. The Ordovician or ancient geography looks completely different from what you know about today, or even different from Pangaea, which most of you will have heard of. The continents were distributed in different ways, and with them the trilobites living off the edge of the continents. And a lot of the work I've done, and I'm not going to talk about it much today, has been trying to put together the world from the kinds of trilobites that we have, living together in one particular continent or another. But it all adds into the richness of the different numbers of species. We had climate change, of course, which can modify the distribution of individual species through time as well. That's just one particular example at the end of the Ordovician. Okay, I've passed over that rather quickly because this isn't really a talk about geology tonight. Let's go back to looking at other aspects of how the trilobites actually lived. The next question is, well, we've got them on the bottom, we've got them in the water column, we've got them at various depths, but what are they feeding on, and how did they actually live in terms of their diets that sort of aspect of life habits. And here we need to turn the trilobite over, which I haven't done yet, to look at something on the underside of the head called the hypostome, which is a big calcium carbonate plate on the underside, at the back end of which lay the mouth. And if you're looking at diet, of course, it's a pretty good place to examine to see whether you've got significant differences from one trilobite to another. So here's the plate. The mouth was here. And when I was studying this particular feature, I noticed there were very different ways in which this plate was arranged on the underside of the animal. And there was a systematic way in which this varied. A has a very, very firmly attached plate, which is very large and occupies a large part of the underside of the head, and it also has a fork in it. Most Trilobite larvae, B, did have attached hypostomes like this, that were attached on the underside rigidly and occupied a large part of the underside. So that it was probably the primitive and original mode for trilobites. However, there were a group of trilobites in which this hypostome became detached from the rest of the exoskeleton to become free-lying on the underside, just supported by a ventral membrane. It was flexible. And this seemed to me really quite an important insight into how they treated their food. So let's have a little closer look at that. Common sense and other features tell you that the ones with the rigidly attached hypostome were likely to have been those which needed to manipulate their food. The legs, whoops, what's happened here? There we are. Remember their legs here, which are actually working against the back end of the hypostome to manipulate and masticate the food. So these ones with large, rigidly attached hypostomes seem to me to be most likely to be those which were predators or scavengers that needed to have a rigid attached plate against which to work in order to deal with larger prey items. And these are just three drawings of different sorts of hypostomes that you find in these forms with rigidly attached hypostomes. They are also extraordinarily varied, which implies that natural selection was working on them very vigorously. So they can be, A is a very primitive one, doesn't do anything very exciting, but you get things with forks in, and you get things that occupy almost the entire lower surface, in fact, in some of the pelagic animals. So I think these were the predatory scavenging type trilobites. They're also all the big ones, all the larger, which fits in very well with that theory. All the larger trilobites I know, including some very big ones on display in the Oxford Museum, have attached hypostomes of this kind. I can't think of any exception to that. Which again makes sense because they're eating more nutritious food and they're at the top of the food chain. This is just to show you some of their hypostomes. Some of the forks get quite amazing. They go along most of the length of the animal. And a lot of them have special features on the back end of the fork, exactly where the food is going to be masticated. This one has a sort of little nutmeg grinder affair, little bobbly thing, so that presumably soft-bodied worms could be minced up against it. The ones with the forks very often have on the inside of the fork little rasps. They do look exactly like files, you know, again used for shredding, presumably they're relatively soft prey items. And these forks appeared several times. That's the primitive one with a very small fork. They appeared at several times independently in the trilobite history, so it's a really adaptive feature. Okay, so these are the animals. We've got to now think of them probably on the seafloor. They've maybe got good eyes, and they're stalking some prey, and then they're going to grab it, and possibly a soft-bodied worm. Annelid worms were extremely abundant in the sediment then as now. And then they're going to grab it, and then they're going to process it using the back end of the hypostome as part of their feeding technique. All of that should leave a trace in the rock of activity. So another line of argument is the tracks left behind by trilobites. That's one of them. These are objects known as Rusophycus, The reason I'm showing you this one is because it's huge. It's about this long. And I've just told you that some of the trilobites with this sort of adaptation are huge, and it's one of the few places. The problem here is finding trilobites and their traces together. One of the few places in the world, in the middle of Australia, where I've done so, there's a huge trilobite with an attached hyperstome with a rasp, and in the same rocks, or very nearby, there are these things. Now that's a cast. Okay, so this is a cast of a hole, and the hole shows quite clearly the bases of the legs, and this part on either side where the legs have been digging in, giving you a sort of scoop. So there's a good match here between trilobite and trace, and there's a very nice one which Derek showed me here in the museum, which is, this is an oblique view, just so you can get a better look at it. The head's this end, okay, and it's slightly tilted down, and I hope you can see that the bases of the impressions of the bases of the legs back here. So this is an animal that's come across its prey, it's stopped, dug down like this, and you can see the busy work it's been doing in the head here to process the prey, and you can even get in the middle here a little picture of the back end of the hyperstome where it was stuffing it into the gut, which passed along under the head and along the length of the animal. So that's the predatory type of trilobite with its attached hyperstome. What about ones with detached hyperstomes? Now, it's very hard to find them in position compared with the attached hyperstomes, not surprisingly. So you have to find trilobites that died on their backs. And these are some. And you'll see when they did die on their backs, this hyperstome just dropped down because it wasn't attached into the head cavity. You can see them lying slightly to one side. So they were loosely arranged. But what they were actually, they had little pivots on, which were operated by muscles. And you can see these little pivots. So what they could actually do is act like a scoop by contracting the muscle because they weren't rigidly attached. And I think these animals did what a lot of arthropods do. They simply processed sediment. They scooped up mud and processed it for organic material. It's a very common mode of life. Organic material is not particularly nutritious, so it's not surprising to find that most of these trilobites are actually very small. But when you find them, you sometimes find them in the myriads. This chap here, for example, is so common, it's been mined in Utah. And most of you who've got trilobite necklaces, I hope you all have bangles, tie pins, will probably have Elrathia kingi from this quarry in Utah on them. This was one of these trilobites, which is found there in its millions. The other thing about this particular thing is, of course, the hyperstome isn't doing anything particularly exciting, it's just acting as a scoop. So through a long period of geological time, those hyperstomes stay more or less the same, all the way from the Cambrian to the Carboniferous. They don't do anything very exciting. Well, you wouldn't expect them to if they're having that kind of relationship to the sediment. But of course, this is a different kind of life from the one I've been talking about, the predator, because you're not just walking along until you see some prey and then grabbing it. This time, you can act as a plow. You can just plow through the sediment, more or less continuously, chomping away as you go, extracting the organic material. And that produces a different sort of trail. Many so-called Cruzianas are of this kind. And I'm showing this one because it's a very beautiful trail, braided trail. This is a trilobite that's gone more than one individual, judging by the size, that's gone through a nutritious bit of sediment several times. It's obviously very tasty. And this is also a rare example where I was actually able to nail the trilobite that made it. This is from Oman, and I was working in the Oman desert. And this was made by one of these trilobites with a scoop-like free hyperstome. So these are the sediment eaters, the kind of the ordinary working stiff of the trilobite world. Then there's a third sort of category. Both the types of trilobites I've shown you so far, both hunters and particle feeders, had the hypostomes which were more or less in touch with the sediment, as you'd expect, or more or less horizontal on the bottom of the animal. But there's another type of trilobite in which the hypostome curves up inside the middle of the head, and so the mouth is elevated above the sediment surface. And this, I think, is a third mode of feeding. This is a wonderful sort of trilobite, the trinucleads, one of my favorite. Wonderful little medallion, quite small, centimetre or two, with these strange fringes on which they rested their head. If you look at a trinucleid from the side, they're actually very convex in the head region, but not in the thorax region. Now, what you've got to imagine here is that hypostome is up inside the head here. There's no way it could be in contact with the sediment. There's no way it could grapple with large prey. What this animal did was have underneath its body a big chamber because of this sort of strange morphology with a very convex head and a very low convexity on the thorax. The underside of the animal had this big feeding chamber. And what did it do with it? Well, it couldn't feed directly on the sediment because its mouth was up in the air. What it did was stir up the sediment into a cloud, a sort of suspension feeding mode, which is again done by quite a number of living arthropods. Now that should leave a very distinctive mark in the rock, because so far we've had walking along, grab the prey, we've had ploughing through the sediment, feeding on the sediment. What about this one? Well, this one will settle down onto soft, muddy sediment. It's got to be like that to stir it up. It's going to feed in one little patch, exhaust that, and it's going to move on to another one and do the same thing all over again. So you can almost conjure up in your mind's eye what the feeding trace of this one should look like. And here it is from an actual fossil. See, there's where those spines rested on the sediment surface, and each side produces a lobe where the sediment was stirred up and from which the organic particles were extracted. And this one, nice photograph of Ken Campbell's, shows one individual that's moved from one place to another in order to process the sediment from different areas. So now we've got a picture of, quite a complex picture of how trilobites lived. We've seen that they could do almost anything that any arthropod could do, except for being a parasite, although even that's been suggested. So there were scavengers and predators, and they were particle feeders, and they were filter feeders, and they lived at various depths, and they lived in the water column. So you can see how they filled up the ancient world. And most of their roles are being taken today by crustaceans, vast majority. And most of those roles are, you can observe just by looking at organisms around our own coastline. So we go some way towards thinking now about how you can do an assemblage with 25 different trilobites all living together, apparently, because you can get different predators feeding on different prey, different particle sizes, and so on. And this was an attempt, I won't go into it in detail, to break down a particular assemblage of deep water trilobites I was working on into those different life habits. So all of this is a very long way round to answer a very simple question, which I'm always asked by first-year students. You know, why were there so many trilobites species? Because they were doing all kinds of different things in all kinds of different places for a long time. Can you take any of these further? Well, I think you can a little bit. Oh, goodness me, I'm using my time up very fast. What shall I do? I think I might just skip past this in order to show you, because I want to leave some time for questions. What I've just skipped past is trilobites that were adapted to living in low oxygen conditions by cultivating bacteria, if you want to ask questions about it later. I just thought I'd go on to some giant trilobites, because I'm working on those at the moment, and Derek and I and others went to see an exhibition which I would recommend to all of you at a place called Arouca in Portugal, northern Portugal, where they've got a Trilobite Museum full of really big trilobites forming slabs. The remarkable thing about this is that many of the slabs just have one species all living together, but my goodness, they're large. They live probably at near the Ordovician pole. This is a slab. You've got a very similar one in the museum here from Morocco, where I've also been working. It's a bit dark, I'm afraid, but you can again see an awful lot of trilobites, mostly of one species, all living together, all dying together. And you'll notice that none of them completely cover up another one. They're all slightly obliquely arranged, one to another. What's going on here? Well, it's my belief that, and this is something I did just last year, that this is probably a fossil example of what we have here with Limulus on Delaware Bay. These animals grow to a full size, where they stop growing, and then they come in to mate and molt. To mate, rather, and fertilize eggs. It's a bit of an orgy. But one of the features of this is that there's a female, gravid female, laying eggs in the sand, and males try to fertilize those eggs by kind of taking possession. One grabs on, but they never succeed. There are usually 2 or 3 others nudging in from the side, as you can probably see here. Now, if you flatten that and squashed it flat, you get something like that, the trilobite assemblage I've just shown you. So I think, this paper I literally published last week, I think that some trilobites probably grew up to a certain size and then went into big monospecific mating assemblages where they'd ceased to grow. And there's various lines of evidence on the actual trilobites themselves that they had reached a maximum size and weren't molting anymore. So this is yet another aspect of the daily life of trilobites, which I'd like to bring to your attention. And just to finish off, some of you may have seen a program with David Attenborough last Sunday, which David and I were in Morocco looking for trilobites like these, which are fantastic discoveries of the last few years, just to show you that we are far from understanding everything about them. This is a trilobite of a genus called Wallicerops, which has quite recently been named, which carries on the front of the head these most extraordinary tridents. There are 3 different species. That one's got a trident with a stem on it. That's got a trident coming straight off the front of the head, and it's pointed, and this has got sort of flattened ones and a short haft. I've no idea what the trident was for. It's a rigid structure, so it was stuck out you know those old drawings of the donkey with trying to get a carrot on the end of a stick. It's a bit like that. So if there was a fish impaled on the end of that or some other edible morsel, the trilobite would never reach it, just in case you were wondering. They're interesting and very curious. From the side, you'll see quite interesting features about them. For example, this one, the haft one, is lifted aloft and then dangles down distantly. Okay, so this could carry it along with no trouble, whatever it was doing with it. But this one has the thing right flush at the front of the animal. You can see big eyes here, so it's a big laterally looking eye, so it's a seafloor dweller. Unless it lifted that trident up, it would have trouble even walking along. So it must have, when it was trundling about, rather like a forklift truck, it must have had the trident lifted aloft in order to move around. And in fact, if you look at it very carefully, and these rather dark slides don't show it quite as well as I'd like, but actually this animal actually has the spines on the back of the thorax here bent to one side, so that when it lifted its head up, they didn't get all tangled up together. So I think this sort of went around, and then whatever it did with that trident, it lowered it down at some point. All suggestions welcome, but I make this at the end because just to show you that there are all sorts of intriguing animals that still turn up. These were only just a couple of years old. There's no sign that we're running out of trilobites. The more you look, the more you find. And some of them are like these, are absolutely fantastic. And that's a point at which I'll stop. Thank you.